So let's start with the SPI stuff. So it used the old names in the past, but now it's trying to avoid these names. But if you look at the chips, it's really difficult to rename all the pin and revise the documents online. Sometimes the documents of microcontrollers are like a few hundred pages. So it takes a lot of efforts, but it's going to happen in the future. But you guys need to know all the names, different names. MOSI, MISO is the old name, the classic name you can find on the documents, but people are trying to use Pico and POSI. Pico is peripheral. Let me see if I have a link. But you search online, you'll see them. Okay. So also it's on the quiz. I think it's question number 7. So PICO, P means peripheral, I is input, O is output, C is controller. So it's just a master and the controller follower. Sometimes it's the leader, follower, but peripheral and controller is the most standard name for now. Try to use these ones. It's replacing all these MOSI and missile here. So you need a leader and the follower, okay, for the communication. And it has one clock and just one wire. So that clock is going to synchronize all the operation. So that's why it's a synchronized. It's a synchronized or synchronous communication protocol. However, UART is not synchronous, and I2C is not because it's just a one wire. So compared to UART and I2C, this is one of the questions on that. SPI is faster. You can run data on both lines, input and output at the same time. So you can run it at a higher speed. Okay, but I2C is slower. I2C is usually a few hundred kHz. So if you do I2C communication, just one wire, it saves a lot of pin source on the board. However, it's slow. So for slower communication protocol, you can transmit the data on the longer distance because it's slow, so it's able to charge and discharge the parasitic capacitance more. It's more capable of doing that. If you're running at a super high speed, we consider all these RC delays, it's challenging to charge and discharge a huge capacitance on the cable. So for our senior sum design this semester, we are trying to design a temperature sensor for the hot tubs and transmit the signal through the cable to the data center. And sometimes the conduits and the cables are pretty long. And that's why we don't want to consider SPI. So because it's too fast. So the SPI communication is usually running at 1 megahertz. So 1 megabits per second, which is pretty fast. Okay. I2C, 400K. UART, you know that. You can change it, right? UART is usually 9600. It's the slowest. 40-year-old technology. And if you look at the pins, this is master out, slave in, right? And this is master in, slave out. And you should connect MOSI to MOSI and MISO to MISO, all right? For the clock, shorter to clock. And this is a chip select. Sometimes they use serial select, but it's basically just a chip select. CS, that's a more standard name, CS. With a bar on the top, which means it's a low active. Low active means whenever it's getting 0, it's being activated. Okay, so it doesn't matter it's a CS or SS, it's just a chip select pin. You have to enable it before you start running this protocol. So if you look at the chart, you may see different chart online, just have a wider data cycle, but it's not, there's no difference on that. It could be confusing, there are so many data lines, but you are able to configure SPICE clock mode by configuring the bits, the 2 bits over here, which is CHPA and CPOL. So CPOL is the clock polarity, and CHP, I think there's a typo here. It's a CPHA, it's not a CHPA. So this is a snapshot from the textbook. I think the typo on the textbook. So it's a phase, clock phase is PHA. It's clock phase. So these 2 bits, the definition is here. This table, I'm pretty sure it is correct, but it's very confusing. You don't have to look into all the definitions and trying to memorize it. So you just need to know, okay? So the clock polarity defines when the clock is idle, what's the logic level is. So for CPOL 0, when the clock is idle, it's 0. So for CPOL is 1, when clock is idle, it's logic 1. For the phase, if the phase, the clock phase, is defined as 0, it's sending out it's taking in that bit whenever it's a falling edge. So 0 represents the falling edge. Remember that. So 0 is a falling edge. So at the falling edge, you take that bit into the receiver. That's the only thing you need to remember. Why that is important? Because you have to write that protocol into a Verilog in order to make it communicate with your microcontroller. So you have different modes. Keep in mind, SPI, you have different modes. For the clock phase 1, the receiver takes the data in. Don't look at these ones; these are confusing for now. So the receiver takes the data in at a rising edge. Okay, so for example, we are doing a 0, 0 here. Okay, so if we configure these 2 bits, give a 0 and 0 to these 2 bits, the clock is idle and it's logic 0, right? If phase 0 is receiving the data at a falling edge, so we look at the falling edge. So it's receiving data at the falling edge. Let me see. MISO, MOSI. I think this chart is not doing really well. I think what I want to do is, let me try here. So for example, this is the clock idle, right? And here's the edges. So the rising edge, it's going to sample the data, and falling edge will take it in. So the falling edge doesn't matter anymore. Okay. So if you look at this, this is actually right. So if you look at this one, so after we go through the code, it's going to be easier to understand this. But now, let's just assuming that the master, so for this line, the master is taking in the data. Okay, at the rising edge, the data is being sampled. You want to sample the data in the middle. So all these lines are data lines. It doesn't matter. It's not defining it's a 1 or 0. It could be 1 or 0. That's why it's having a 1 and 0 in there. So it's just a data lines plus. Okay. So we want to sample the data in the middle of it, so we get a most stable data point. It's not getting closer to any of the edges. At the edge, sometimes it's getting a ramp here, so it could probably sampling here. Then sometimes you don't know it's a 1 or 0. This is still 1, but what about your sample here? Okay, so that's why to get the best result, especially if the digital data is running so fast, you want to sample right in the middle of the data. That's why here you sample it here, right, at the rising edge. And the falling edge doesn't matter because it's already sampled. It's already sampled, it's already on the data line. Then the falling edge will take it in. So the receiver will take it and put it in the register. Okay, so sample it in the middle and put it in the register at the falling edge. So they are all defined in the code. If you look at this example, so the leader transmitter, leader is a master, is a controller. Okay, so leader, master, controller is the same stuff. And follower, slave, you know, and what is the other one? Peripheral, right? Peripheral. They are all the same thing as well. But now we, you know, the textbook use the leader and follower, and the most standard in the industry is are using peripheral and controller. So controller is this guy, leader, okay, and follower is here. And if you look at the chart, when we are trying to write the logic for the two modules, because you have a leader, have a follower, and you need a digital block for 1, 2, 3, 4 actually. So MOSI for the leader and for the follower, and also MISO for the leader and follower. So you need 4 digital blocks. So you need 4 Verilog modules to define all the blocks. So if you look at the code here, these are 2. Okay, that's the 2 of them. One is a leader transmitter. Another one is a follower receiver. So if you look at the chart here, could you let me know which one we are writing right now? Leader transmitter and follower receiver, which modules we are designing in that example? Or master transmitter and slave receiver right now? Which module we are writing right now for the pins? Yeah, so it's MOSI, right? Because transmitter is out. So sending out, transmitter is sending out, receiver is input. So MOSI is going to be the module right behind this pin, and also the module right behind this pin. These are these 2 modules. Okay, and for the following ones, I believe we have, so that's follower transmitter. So that's MISO, right? So MISO missile. So this is sure provided 2, all the 4 modules for the communication. So let's look at the first 2 first. So I'm going to let you tell me which one defines a clock. Because for the SPI communication, you can define the length of the bit of the data. It doesn't have to be 1 byte. It could be longer, could be shorter. And it can define the speed as well. So if you think about the communication diagram, 4 data lines. All right, so the clock is synchronizing the communication of the 2 modules. So it doesn't have to follow like one specific frequency, right? No matter how, so sometimes we are trying to operate a D flip-flop, just use the switch. We can even use a switch with our fingers to provide a clock. It's going to work. It's a sequential circuit. No matter how fast you operate it, it's going to running following the rising edge or falling edge, no matter how you define it in the Verilog. It's the same thing as your SPI, right? If you have a clock synchronizing the operation, you can even use a switch to run the SPI communication. Okay, but now we are trying to make it faster, and you can run it at somewhere around 1 megahertz or a little bit higher than that, but usually 1 megahertz is the standard rate. But we have a 100 megahertz clock on the board, so we can divide it into 1 megahertz. But you can see this example is running at 2 megahertz, it's fine. So just let you know you can run it at 1, 2 megahertz, doesn't matter. It's pretty fast. So the leader or the master has to define the clock, the serial clock. So when I'm talking about define means it's defining the rate of the clock. So I have to have a counter here. So whenever it reaches 25, I flip the clock. So it's actually 50 cycles per second. So you use 1 megahertz divided by 50, you are getting 2 megahertz. So this is how you get a 2 megahertz clock, by dividing the 100 megahertz frequency by 50, right? So you can see I have an ICK signal line in the leader, and definitely you need a ICK line in the follower as well. If you look at the follower, I do have an ICK line, but do I define it? Do I need to define it here or specify the details of the ICK in the follower? Do I need to do that or not? It's just a one line. It's one metal piece, right? If you define it in your leader, the leader is going to drive it up and down, right? Drive it with a certain frequency. Then the follower just use it. It's just a clock being used for all the operations. So that's how you get everything synchronized. So you can see it's directly using ICK. Whenever it's a pass edge ICK, it's going to do all the following stuff. Okay. So as we said, the C phase here, the clock phase, defines at which edge, falling edge or rising edge, the receiver takes the data in. Okay? So my question for you here is, for this configuration, which mode I'm running this SPI on? Is that C clock phase 1 or clock phase 0? So the clock phase defines at which edge the receiver takes in the data. 0 is the falling edge and 1 is the rising edge. So for this one, C phase should be what? 1, right? Why does this matter? So you can program it, and after you synthesize it and put on IPGA, it's already configured. It's not fabricated, it's already on the hardware. You cannot change it, right? So however, if you interface this guy with Arduino SPI, if the Arduino has a built-in SPI, you have to configure the registers to make the right mode, make it running at the right mode in order to communicate with your ASIC, which is application-specific IC that are designed on the IPGA. So this is a part of the course project. Okay? When you communicate with Arduino's SPI, you need to look at the data sheet and configure all the phase and clock polarities. Probably not clock polarity. I don't know if you need to do that as well. Maybe. But you can always change it. You can either change it here in your ASIC, your chip design, or you can change it in Arduino settings, which is just the software. I believe there's a register that it can write in, and that is able to control the configuration of the SPI mode. Okay. And does it make sense that I have a negative edge SCK for the leader? Do they share the same clock? Do these two modules share the same clock? Yes. So does that make sense to have a negative edge SCK? Can you have a positive edge SCK here? So what is this one doing? You just think about it, okay? So the metal line is just one metal line, it's one voltage node. If the leader do something to the node, the receiver will see it. Okay, just one metal line. So in that case, the leader is doing something to the, so all the following ones, you don't have another clock edge, right? So whenever the negative edge arrives, it's going to update everything. And then do what? So SPI is really simple, right? So whenever during some event, could be a rising edge or negative or falling edge, okay? Then you just put the data to the bus, to the line, right? And then the receiver receive it at a different phase. That's it. Very simple. That's how you do the communication, right? So so it's all being synchronized by the clock. So does it make sense to have native edge SDK for the leader whenever you have a pass edge SDK for the follower? And why? By looking at this, what's really happening? Or this, doesn't matter. You can look at this, even this chart or the timing. It's one cycle. It's just one clock cycle. Every clock cycle has one rising edge, one falling edge. So I have to put the data onto the line first. Then it's ready. Then the receiver will take it in, right? So that's why it has to be different edges. Okay. So that's why if you look at this one, you make the data available for a while, and then the rising edge, as a rising edge, the leader will put the data onto the line. Okay. And then the falling edge is going to take it in, so the follower will take it in. I just following the protocol. So it's like I put it onto the data line, and then the receiver at another edge just take it into the register. So if you look at the timing here, does it matter that the falling edge, the data is changing? It's at the phase that it's changing to another cycle. Does that matter? Yeah. So the data is not being put into the line by the leader. So the data is changing. It's changing in where? In the leader. It's not being put on the line, so it's okay. So the line is still holding that data for the receiver to put it in, even though it's changing here, but it's not changing on the line. And that's another example. To the missile line instead of the MOSI. So the example for this tutorial, I think is provided, is it? So the code is not provided, but these are the modules you can use for this application. I think all these modules are available on the textbook. You can find the textbook. These are all provided. Put them together, create a top module, and do the connections. It should be able to read the light intensity in the digital mode. Okay, so this is the light sensor. I have it here, so everyone will grab one. So the light sensor is on the little PCB and it has a standard SPI cable on it. So it's a 3-point servos logic, so you can directly use it with a FPGA board. So we never had any big problems with this example. It's pretty simple. And the course project. So this tutorial, the SPI tutorial, is due next Thursday. I'm going to give you guys a week to work on that. And the course project is a digital sensor SoC. So you can see the computer engineers works for Xilinx. They are able to design a digital sensor like that, right, and sell it. We should be able to do that as well, even though we are not trying to tape it out, but it's going to be the same stuff. So the sensor has, this is a question to ask you guys probably. So what do we have for this type of sensor? So they make the digital pin available at the output of the sensor to make it easy to communicate with microcontrollers, right? It just has the SPI. You hook it up to the SPI port of the Arduinos. You can directly get analog data on the serial monitor. So the light sensor is an analog device. No, the light sensor, it could be a photodiode. Okay, so the photodiode receives light, like the camera has little photodiodes in the pixel for each pixel, right? It receives the light intensity or light signal and convert the light into photocurrent. And the photocurrent runs through a resistor and the current is being converted to voltage. So the voltage is being amplified and then being digitized by ADCs, analog digital converter, and then you get a digital signal. It could be 8-bit, 10-bit, 12 bits, depending on the resolution of the ADC. Okay, that's a workflow. Then you got digital data in parallel. So you put it into the SPI mode module. So it's going to take in that parallel data and then transmit through the serial line following a certain protocol. In this example, we are using SPI. So that's how we design a digital system or SoC, system on chip. So this is one of the examples, right? So this the computer engineers design this kind of sensor. It has a photodiode in it, and has amplifiers, has ADCs, and eventually it gets into the SPI, which is the module we are going to use for this tutorial, for the last tutorial, and eventually send it to the foundries, for example, Global Foundry, TSMC, Samsung, whatever, to fabricate a chip, and you put a chip on the PCB, and you mounted some other like power modules on it, and you put the pins on it, right? Ask some students to solder the chips for you. It's all fabricated in the foundry, and you can sell it, right? Probably $4 for each. If you fabricate maybe 4 million of them, you are still making a profit. Okay, so the sensor we are going to design is a analog sensor as well, but we don't specify what kind of analog sensor we are going to use. I don't think it's feasible to complete everything, including the amplifiers and filters. So, but you need to know, as an electrical and computer engineering student, you need to know that you need to pre-amplify the analog signal and filter out the offside, the noise, and everything, and bring it into the range of your ADC's range. For our example, it's 0 to 0.0 volts. So the analog voltage, the variation, it could be temperature, could be light, could be a lot of things. They have random offset on it. It could be an analog signal sitting on like 1 volt, swinging around 1 volt, 2 volt, 1.5 volts. It's all possible. And the voltage range of the signal could be, 100 millivolts, 150 millivolts. So you need to filter out the offside first to bring it down to 0, so it's swinging around 0. And then use the middle voltage. For this example, it should be 1.25, 0.3 divided by 2, it's going to be 1.15, right? 1.15 volts. And you need to amplify the signal only, not the offset. The signal only, so it's swinging around 1.5 volts. But the signal, which carries the information, is being amplified to occupy the entire dynamic range of the input of the ADC to use all the resolution. You don't want that the signal input to the ADC is swinging around like 1 millivolts, right? You need the signal to occupy the entire range. So anyway, so we are not doing the pre-amplification part of it. It's going to take probably 2 weeks for guys just working on that part. So we're assuming the signal is already amplified and perfect, occupying the entire dynamic range of the ADC. How do we do that? We use the serpent servos as the power supply of the potentiometer and ground it. So definitely serpent servos analog voltage. So you turning the knob, and definitely you can change the voltage input from 0 to serpent 3. Does that make sense? Okay, so voltage input, just a potentiometer. Okay. And the basis 3 has an ADC on it, has 16 channels. However, if you open up the constraint file, these are all the pins relevant to the ADC. But you can see the numbers are like 6, some random numbers, 6, 7, 14, 15. That's it. I was wondering why. I mean, you have 15, which means you should have pin 0 to pin 15, but only has 6, 7, 14, 15 in there. So these are over here, I think, pins available. And they labeled them in the different name as well. But I believe these are 1, 2, 3, 4, I think. You can find out the map for these ones. But these are the analog pins, the ADC pins. Why is that? What do you think? the chip has 16 ADC channels. So which means you can connect 16 up to 16 analog inputs to the chip to do the ADC converters. Right? It's pretty powerful actually. It's a lot of ADC ports. So where are the pins? Where are the pins? It's underneath the chip. So the package is one of the advanced packages. You don't have you don't need to solder all the pins like surface mount pins on the edges. So they are all underneath it. They are like all the little circles, the pads. It's occupying the entire bottom part of the package. So you can integrate more pins on it. And also it's taking less area because it's all underneath the package. So you are not taking space outside of the package of the chip. Reducing the footprint of the chip on the board. Even though we don't need it that to be that small on this IPGA port, but what if there's a company want to use this chip, they don't want to tape out their own ASICs, they just want to use IPGA like what we are doing here, just put a core on it, put the ADC, the peripherals and everything on it, and then just sell the IPGA as an integrated circuit. Another side question, so what's the difference if you tape out your own chip and compared to like you buy chips from AMD or Xilinx right now, or Xilinx or AMD right now, and writing Verilog and synthesize your design onto the IPGA and sell the IPGA compared to the dedicated chip you design and fabricated with TSMC, for example. What's the difference? The cost. Yeah. So I have to buy, if you do IPGAs, I have to buy these chips from AMD first, right? But if you fabricate and use a foundry, it's cheaper if it's a large volume. And so this one has a lot of pins, right? Has a lot of pins underneath it or on the bottom of the package. However, you don't have that many headers here. So the headers are taking a lot of space. And you want to make a board, so you can see the board is ready, having everything on the switches and GPIO pins and USBs and VGA. You don't have more space. So I believe they have more analog inputs of the pins on the pads at the bottom of the package. However, they didn't connect it to any of the GPIOs. They don't have space for the GPIO on the board. You know what I mean? So that's why they only used they only connect the 4 of them to the headers. So that's okay. We only use one. You see, a lot of people they don't need to use that many analog channels for their application. So we have 4, and it's really interesting. I don't know if you guys have already taken. It could be in circuit 1 or in analog. It covers the amplifier configuration. It's called difference amplifier. It's taking a differential input. So you got op-amp, right? You got 2 inputs. It's actually not making a difference. You could have 2 signal lines, or if you ground one of them and get a signal input to the other one, it's actually taking the difference of the 2 inputs. So you use this one minus this one as a voltage input. It doesn't matter. Let's just ground one of them. So for example, we have, if you are using the auxiliary pin 6, why is it called auxiliary? It's because these ADC inputs could be used as ADC inputs. Also, they can be used as general GPIO pins, digital pins. Depends on how you configure them. Okay, and there's another analog input pin. It's called VN in and VP in. That's another pair of differential inputs. They are doing the similar job. But these 2 pins are dedicated ADC pins. Keep in mind, they cannot be used as a general purpose GPIO pins. However, do we have them in the constraint file? No. So they are probably 2 pins of the chip, but they are not being connected to the header, so we're not using them. So don't care about that. You don't have to care about that. So you just pick up one of the auxiliary pins as an ADC inputs. So, for example, if you pick up number 6, you got the positive pin 6 and the negative pin 6, and ground one of them, and have another one as a It's taking in the input from the potentiometer here. That's how you give the input to the IPGA. And then you have your SPI modules in the chip, in the IPGA chip. So the ADC, I was looking at the instantiation. There are a few examples. I provided a link over here to see the ADC demo. That's an example published by Digiland, which is a company fabricated all the Xilinx FPGA boards, and it has a example of the ADC demo. And if you click this one, you can see the GitHub example here. Source. I don't want to download it. Let's just look at from online version of it. So go to source, go to HDL, hardware description language. You can see all the Verilog models, modules, and the ADC demo. And you can see these are the keywords, right? These are the pins from the constraint file. So you don't want to change it. And clocks, they have a different name. You are using this name, you have to change accordingly in the constraint file. So as you know, we are using just clock, simply just CLK, right? Anyway, so these are the pins, and these are also instantiated, but they're not being used. I don't know why they still have to do it. And scroll down, you can find out the ADC module. It's a block. It's like other blocks or unit under test, UUTs. But you can see it's a wizard, so which means it's being created from the IP available in Vivado. Okay, so don't have to create the ADC module ourselves. It takes a lot of time. But if you really want to do that, the way to do that is go to the ADC's user menu, which is here, the user guide. And you can find out all the design, the technical details of the ADC. So for example, let's click the, so I'm going to do a really quick search. Instantiation, for example. Okay, how to instantiate that ADC module in your top module. And they provide example here. ADC instant. And these are all the pins of the ADC. Okay, and you can look at if you want to know what are the pins available for the ADC, there's a design block of it. And these are descriptions and explanations of the pins. And another thing you need to know is the configuration registers. So a lot of times when we program you probably have done that in your RAM control class, right? So you have to configure a register before do something. For example, interrupt, activating an interrupt, you have to turn on activate the interrupt enable pin first. So these are registers available. So you can see these are 8-bit registers. So explore that a little bit, see what are the registers you need to configure before you run it. Okay. So this is how you configure them in Verilog. And it has a temperature sensor on the board, but we are definitely not doing any temperature sensing of it. So you can just ignore that part of that user guide. And you also need a level shifter because the basic 3 board is 3.3 volts logic and your Arduino is 5 volts. So level shifter, I do have a lot in the lab. I've used that for I2C communication, which is slower. But if you are doing a 2 microhertz communication, you may need a faster level shifter. I just ordered it. But I think to start working on this project from scratch, you want to take baby steps. Okay, so what I would do is, for example, since we have never worked on the ADC in the past, so why not just use a potential meter, right? So connect potential meter to the business array which has the ADC on it, and then just to show the digital output of the ADC to the LEDs. So when you turn the knob of the potential meter, you are changing the voltage input, so you can see the digital output on the ADC on the LEDs in real time. So if you turn the knob to one end, to one terminal, to just probably clockwise, for example, I don't know which one, depends on how you wire them up. If you turn it clockwise until the end, it's probably, for example, it's connecting the potential meter's output to 0, right? So the LEDs should be off, should be 0, shown 0. If you turn it all the way on, it should be all ones for the LEDs, 0.0 volts. And the digital output for the ADC, if you look at the example code here, I think that's on the, oh, I don't have it here, sorry. So the digital output is 16 bits, even though the ADC is a 12-bit ADC. But the output is 16 bits from 0 to 15. So if you directly connect the digital output to the LEDs, it's able to handle it. So directly connect all the pins to it. So if you are giving a 0.0 volts as the input, analog input to the ADC, it's actually giving you, so you can expect 12 LEDs are being turned on, and got another 4 LEDs on the left-hand side are just off because it doesn't have that many bits for the resolution of the ADC. So do that first, I think. So I haven't written down all the partial credits for each step, but I think if you guys finish that step, I'm going to give you at least 60 to 70% of the credit for this project, since we haven't done that in the past. Is that fair? So SPI, integrate SPI into it. So the SPI will be taking the digital input from the ADC. So I encourage you guys to form teams, 2 people on a team. So while one person is working on the ADC, another one can write the interface of the SPI, assuming you already have the data input, the 16-bit data input to the SPI, okay? And the SPI takes in the data and put on the line. And also have to work with the level shifter. It's really simple. Level shifter is super simple. I think I have a link here. This is the one just ordered today. But I do have the level shifters that I used for I2C in the past. Hopefully it should be able to handle SPI speed here as well. But if you look at the pin out of the PCB, it's really simple. You have the A lines and B lines, right? So one side is input, one side is output. So one side is connected to the lower voltage, one side is connected to the higher voltage. The Arduino side is having 5 volts and ground, right? They should be sharing the same common ground. So for example, if you look at this board, if I connect the B ports to the Arduino side, A ports to the basis 3, the IPGA side. So VB should be connected to where? VB. The VB pin should be connected to where? Five volts. Because the B ports are connected to Arduino. So you need a 5 volts as a power supply for the high voltage side. UR directed to the serial monitor. No. We are trying to do the SPI interface with the Arduino. You know what I mean? Good attempt though. So what about VA? Yeah. So all the logic running on the A side will be 3.3 volts logic and with a 3.3 power supply. On the B side is going to be 5 volts with a 5 volts power supply. And they are sharing the same ground. And I believe the ground GND pin is a common ground for both sides. And the OE should be some sort of enable. Just look at the data sheet, see if it's low active or high active. You probably need a voltage high, 5 volts, 0.0 volts, 5 volts. Probably it's low because low is common low, right? It could be it doesn't have a bar on the top. So I'm not really sure. It's easy to figure out by looking at the data sheet. So that's the level shifter here, and Arduino. So there's something I want to, let you guys know for the Arduino programming. You probably have never done it in the past, which is called register configuration. So you can do that easily with assembly by just assigning a hex number to the register. But now we are handling the C language, and if you see something like this, you should understand what's going on. So in the past, for the PIC microcontrollers with microchip, they can do the register name and dot. You know what I mean? So, for example, that's the register name A, okay, and dot 1. So 1 could be the bit 1 of the register, and you assign a 1 to it, so you can assert that bit in that byte, in that register, with a 1, with a logic 1. That's the older convention of programming the configuration, the bits of the configuration for the registers. However, in Arduinos, it's different. So you are doing a shifting. So put a 1, and you shift it by a certain number of bits. And why that works, I'm going to show you really quick. If you look at the data sheet, that's Atmega 328P chip, which is a chip being used for the Arduino Uno's board. And you can find out the register manages all the configuration for the SPI port. It's called ISPCR. The ISPCR register is an 8-bit register, controls the functionality of the SPI. Okay, so if you look at the bits, some of the names are pretty familiar with us. CPOL, CPHA. So what are they? Yeah, polarity and phase. Can you configure these 2 bits in the SPI module in the Arduino chip? Yes. You just write a 1 or zeros into these 2 bits. You got that SPI's mode configured. Okay. So I think this tutorial showed you how to configure SPE or MSTR. These are 2 different bits in this configuration register, SPE and MSTR. And you can read the document to find out the functionality of these. Okay. However, if you don't do anything to other bits, what are the default values? So when you write programs, zeros. When you write programs with Arduinos, have you written configurations of the registers? You haven't done that before, right? Unless you took my controllers, you probably did it for the interrupt activation. But for most of the code we have written in Arduinos, we never do anything with the configuration of the registers. So usually they just, by default, just zeros. So if you don't do anything with the clock priority and clock phase for this register, what are they? Zero. So it's a falling edge. It's a falling edge taking in the data. As a falling edge, it's a 0 as a idle state for the clock. So in that case, if you don't configure these 2 bits, you have to make it right in your Verilog, right? So in your receiver mode, is your basis rate receiving or sending? Yeah. So do you need to do anything to it? So it's associated with some of the sending mode in the register, right? Have to look into that. So if the Arduino is receiving data at the falling edge, your sender should put the data on the line at the rising edge, right? In IPGA. How that works. So ISPE, the ISPE keyword in Arduino's IDE is what? What's the number of it? ISPE's number. 6. If you shift 1, so what does this do in C++? What does this do? 1 shift. You are shifting a 1, just a number, just binary number. You are shifting 1 to the left. You are shifting 1 to the left by 6 digits. What is that number? So 1 is initially here, right? 1, 2, 3, 4, 5, 6. So that little 1 will be shifted to this spot. So you are getting an 8-bit binary number has a 1 here. So what's going to happen is you are having a 0, 1, and all zeros, right? That's what this one does. Okay, and it or this guy, MSTR is over here, number 4. So it is this one. So by doing this, you are getting 2 bytes. And these 2 bytes are these 2 bytes. And they are being ORed together. And eventually, you are having the 2 bits at these 2 locations are getting 1s, and all the rest are zeros. It's a bitwise OR. So eventually, you are getting a 1 byte as a configuration code for the register, and you assign it to this register. So in that case, you are able to assert these 2 bits in that register for this configuration register to get the job done. So similar operation with other bits as well. Is shifting a 1 to that location and do an OR logic. Bitwise OR logic. Is that clear? Okay. So obviously you need to configure the register in Arduino before communicating with the basis report. So if you have 2 people on the team, you can split the tasks, right? So one works on the SPI and ADC, one works on the Arduino level shifter and also the analog input, whatever. Was a reasonable way to split it. And we are going to have a presentation on probably the last day. It's going to be the week, so 25th, Thursday. During the lab time. Okay, because we have a longer time over there to have a presentation of the results. Is it? So 2 weeks is going to be this week and next week, right? So this is 3 weeks from now. No, the 2.5 weeks from now. Then we can do it on the final exam day, so we don't do final exams. Is that fair? So I don't have to grade the exam. I like you guys to work on more hands-on stuff. You can get a job instead of working on paper. But you still have to turn the quiz. All right. If we do a final exam, it's going to be another IPGA project. It's a bit too much. Okay. So the exam day, I think the exams are 2 hours time blocks over there, right? So I have enough time to do the final presentation. I got more time to work on the project as well. And there's another task we have to do according to ABAD. This one covers all the 7 criteria of the ABAD outcomes. So that includes problem solving. Definitely, we solved a lot of problems. Box checked. Design. All the tutorials don't really have a lot of design stuff in there, but the last course project is the design project. And The third one is communication. You write reports. I grade your reports, and you have a presentation, so oral and written presentation. And number 4, ethics, professionalism. You failed? No, I'm kidding. So we have this task to examine that part, that aspect. So it's going to be a few questions. I'm going to give you a quiz on that. One of the days in next week, probably. We'll do the quiz, number 9, I think, for the ethics questions. Number 5 is teamwork. So course project, you have 2 people on the team, teamwork. So I would grade that, okay? If one of the person is not really functioning on the team, it's probably not getting a good score on that. And number 6, experimentation. We did a lot of experiments. We have labs. Number 7 is lifelong learning and new design or that kind of stuff. So without specific instructions, you guys still able to find out the solutions online, which is what we do for the course project. We haven't done ADC, so you guys learn how to do the search and look at the data sheet. Probably, hopefully, you'll learn how to do that throughout the semester. So hopefully, you can find out enough details from the menus and find a solution for the ADC part. Okay? Any questions? You can work on that today. I think I already answered most of the questions. Did I? I see the first question, easy. Second one, easy. Third one, easy. You'll pay attention to it. I just said that. Number 4. Yeah, I talked about that. Number 5, I did that. Number 6. Could you connect multiple peripherals to one controller? Yes. Number 8, easy. Number 9, easy. Okay. Could you turn it in before 12:40, or now if you want? You want to revise it, or you want to redo it? No? So confident.